origin somewhere. So you understand that for choosing the origin, we know that we should choose that origin which does not contain the plane, right? You should not have a plane contained in that origin. So for example, if I choose this plane, this as origin, this plane is contained in this origin. So this is not the right indication of choosing the origin. So I have to choose some other place for origin. So for example, I choose this as an origin, right? So this is my origin. From origin, I have to see what are the intercepts on x, y, and z. On x, we have a -1 intercept. On y, we have no intercept, because if you see, it is parallel to the y-axis. The plane is parallel to y-axis, so you have no intercept on y-axis. And on z-axis, we have one intercept because it is cutting it here. So this is your 1, positive 1. So you have a plane, you will call it minus bar 1. So you'll call it something like this. You will call it bar 1, 0, and 1. This is your plane. And this was 100. Is it clear? It is important to know where you have to choose your origin, and then accordingly you can put the indices for the plane. Okay. So we'll do the next question. The next question is find the angle between plane 100 and 111. So you have to find a plane. You are given two planes in a cubic system. You can try to also draw these planes in a cubic system. So for example, if we have this is a system for which we want to draw these planes. So 100 will be, if this is the origin, 100 means there is no intercept on y, there is no intercept in z. So this is your plane, this, right, the front portion, and you have to choose what is the 111 plane. So 111 will be 1. This is x, this is y, and this is z. So you have one intercept here, you have one intercept at y, you have one intercept at z. So it is something like this. So you have two planes, this plane and the plane which is at the front. You see there is some angular inclination between the two planes. So they are not exactly parallel, right? If you see, there is this 111 plane and 100 plane. They are not parallel, at least. There is some inclination between the two planes. So you have to find what is the angle between the two planes. So how will you do this? Whenever you have an angle, you have to find any angle, you have to use the formula for between them, that will be given by cos of theta, that is equal to dot product of their planes, right? So that will be h1 h2 plus k1 k2 plus l1 l2. These are dot products and square root of their planes, the squares and square roots of their planes. So this will be h1 square plus k1 square. This is how you give the angle between any two planes. L1 square, and that will be multiplied by h2 square, sorry, yes, h2 square plus k2 square plus l2 square. So you can find the dot product first. Dot product will be 1 dot 0, 1 dot 1, that will be 1, and the rest of that will be 0. And then we have under root of h1 square, k1 square, l1 square. So that will be under root of 1. Then we have for this, that will be under root of 3. So we have cos of theta equal to 1 by root 3. So can you tell me what is the angle for between the two planes? So what will be the answer? The value of theta?
54.73.
Okay, so your option C is your right answer. Okay, and that will help you in giving a angle between your plane and your like this is can also be done for a plane and a direction. So, for example, if you are given a direction instead of 111, you are given a direction of 111, right? But you know the perpendicular of the plane is given the direction is given by the perpendicular to the plane, right? So your plane will be the same. So you can also help it will also help you to find direction between your planes and direction between two planes or between two directions. So the same formula will be applicable. You should always remember that if you have a plane, the perpendicular to that plane will be the direction of that plane. So that can also be helpful. So we have another question that says, does the 122 direction lie in the 301 plane? So you are given a plane, you have a plane of 301, and you want to see if this direction 121 lies in the plane. What do we mean by lies in the plane? Say for example, we have this plane which was 100 for us, but it has directions in it also. So this is one of the directions that it contains. This is also one of the directions it contains. If you choose this origin, this as origin. So these are the directions that it contains. The boundaries of the plane make the directions of the plane. So you have to say if this direction lies in the plane. You have to again rely on the same formula, the cos of theta, that will help you to determine whether it lies in that plane or not. So first you try to attempt the question and then we can do it. The condition for a plane or a direction containing in the plane is that your cos of theta should be equal to 0, right? So you have to find the dot product between the two. So what will be the dot product? 1 cross 3. So you'll have 3 plus 0 plus 2. So that will be the dot product between the two, and it is not equal to 0. So if it is not equal to 0, so you have to say cos of theta is equal to 0. Sorry, I just wrote it one. It is actually cos of theta should be 0. Then only you can say that the direction and the plane are direction lies in the plane. So here you don't have theta equal to 0. So the dot product equal to 0. So then you can say thus the direction does not lie in the plane. So no is the right answer. Then we have another question on Bragg's law, which you have done for XRD or X-ray diffraction. It says that the longest wavelength that can be analyzed by a sodium chloride crystal of interplanar spacing 0.281 between its principal planes in the first order is. So you have to say what is the you are given the d spacing, right? You are given the interplanar spacing. You have to find lambda, the longest wavelength that can be analyzed by NaCl crystal. So this will help you to determine that what kind of a crystal you should utilize in your XRTs, right? So if you know that you have for example, you have a sodium chloride crystal and it is having a certain d-spacing. So this is your material that you want to analyze with certain d-spacing. Now you should determine what should be the wavelength of my source in this X-ray diffraction that will help me to analyze this this interplanar spacing. So that is how you fix, like for example, usually the copper is the source of in X-ray diffraction or molybdenum is used. So that will help you, that is very important because that will emit a characteristic wavelength. Say for example, copper emits some characteristic wavelength that will be different from molybdenum. So whenever you are doing an X-ray diffraction experiment, you should be aware that what is the source that is being used for your analysis of your sample. What is the wavelength of the sample source that you are using for determining your sample characteristics. So that is on what basis this question is based on. So using Bragg's law, you can find the longest wavelength. You can try to answer this.
I'm getting an answer 0.562.
Okay, so this is
But none of
point.
the option is available here.
Okay, so maybe we have some, like you can see this option point B is closest to that, so 0.56. Maybe we can,
Okay, ma'am.
there could be some error. So we can first try to solve it. So we have some, we are saying that the longest wavelength we have to determine. So first we know Bragg's law says 2d sine of theta is equal to the n lambda, right? But you are saying that it should be in the first order. So this is your n is equal to 1, right? Now you have to find this lambda. You are given the value of d, and it is saying it should be the longest wavelength. So if you have a longest wavelength, that means sine of theta has to be equal to 1, or theta has to be equal to 0. So this is equal to 1. So we take overall equation as 2d is equal to lambda, right? And then we have to find lambda only, that is 2 multiplied by 0.281. So that is 2, 6, 4, 5, sorry, 0.562. I think nanometer, right? Nanometer. So then we have another question on Bragg's law that says that the wavelength of X-ray used in X-ray crystallography is 8 into 10 to the power minus 10. It undergoes first order reflection at a glancing angle of 4.59. What is the spacing between the atomic planes? The spacing between the atomic planes is nothing but your value of d. Again, using the value of same 2d sine of theta, n of lambda, n is equal to 1. We know the value of theta is here 4.59, so you can write as 4.59. Okay, and you have the value of d, so you have to find what is the spacing between the atom planes, so d, and you have this angle of lambda, that is 8 into 10 to the power minus 10. Okay, so you have all the values, you have to put it in the equation to find d. So d will be equal to your wavelength, that is 8 into 10 to the power of minus 10 divided by 2 multiplied by sine of 4.59. So that is value of your d. So you can try to calculate it.
Ma'am, why we have taken theta equals to 4.59? Should it be taken half of that value?
No, we have a glancing angle is actually the angle of incidence.
Okay, ma'am.
Yes. I think maybe I can also try to solve it. So it is 4 sine of 4.59. I think the answer is somewhat 4.9 multiplied by 10 to the power of minus 9 meters. Okay, this is the value of your d spacing that the X-ray source can deduct. Okay,
5 nanometer.
really, yes, 5. Then we have another question. This is an important question for your diffusion. Right? Diffusion, we have done some similar question earlier also. So we will try to do it again. So we have a diffusion couple that is composed of two silver gold alloys, and these alloys have a comp. So we have two alloys. So we can say we have, say for example, this is our alloy 1, this is our alloy 2, and you are forming a diffusion couple between the two. And you have composition of 98 and 2. So I'll write like this: 98 silver, 2 is gold, and there is also this composition for this, it is 95 and 5, right? So you have to say determine the time this diffusion couple must be heated at 750 degrees Celsius. So you are heating it at a certain degree of temperature. You expect whenever you are heating a material, you expect diffusion to take place. Once the diffusion takes place, you have some movement of the ions from some higher concentration to lower concentration. Okay. So here you have a silver rich concentration. You have a gold is rich, right? So when we are saying that you want to achieve a composition of 2.5, this is the composition that is to be achieved, final composition of 2.5 at a 50 micrometer position into a 2 weight percentage gold side. So you want, because obviously your gold atoms will be diffusing from this side to this side to form a equilibrium between the two. So what will happen, you will have some intermediate composition which is here 2.5, yes. So 2.5, and it is at a distance you want to achieve it at 50 micrometer, right? So this is your 50 micrometer. So with the diffusion of the gold atoms into this alloy 1, you will have a concentration of gold somewhere in between 2 and 5, and that will be 2.5, and it is at a position of 50 micrometer in alloy 1. So this is something that is given in the question. And you are also given pre-exponential values for gold diffusion in silver, that is 8.5 and 20 to 100 joules per mole. So you have to find that what is the, like you have to find the time that will be required to diffusion to take place, right? So you have to find T. Initially, if you have remember, we have done some similar equations, and you remember we have some formula where we have a concentration X which is at some intermediate concentration that is equal to the sum of the concentration. So I'll just write the formula first: C1 plus C2, the two alloys concentration at the two positions, divided by 2, and we had another part where it was the subtraction of the two concentrations. I think it was like this: C1 minus C2 divided by 2, and then we had some function of ERF, right? This was under a non-steady state condition, divided by under root of dt, right? I think it was 2 dt, 2 dt. So this is the concentration at certain position X. You know the initial concentration of the two alloys. You know this, all of it. This is the ERF function. You know, you have to know this D, which is diffusion, but you only know the actually the pre-exponential and activation energy for the equation, right? So you know D naught, you do not know the actual D. So you know the diffusion coefficient is actually based on D is equal to D naught e raised to power minus Q by RT, right? This is something that we have equation, and you know this D naught here, you do not know this D. So you have to find first diffusion coefficient in order to use this equation, so that we can find the time that is required for diffusion to take place. So first you will use this equation, which is D is equal to D naught e raised to power minus Q by RT to find D. So you can put in the values. D is equal to first D naught, so D naught will be equal to 8.5 multiplied by 10 to the power of minus 5, right? And then we have exponential of, I'll write it like this, exponential of minus Q. Q, you know that the activation energy that is given here, that is equal to 20 to 100, and then you have the value of R, that is your 8.314, multiplied by the temperature. So what is the temperature? That is 1023.
Ma'am, excuse me.
Yes, yes.
Ma'am, in this formula, D is equal to D0 e raised to power minus Q upon RT. Should we put the value of R in joule? You have put in kilojoule.
No, 8.314. That is joule only.
Joule or kilojoule, ma'am?
That is joule.
Okay, ma'am.
8.314 is the unit of K in joules per Kelvin mole per mole. So you can put in the value and then tell me what is the value for D. बताओ.
Ma'am, 4 into 10 is to power minus 15.
The value of D, right? 4 multiplied by
10 is to power minus 15.
okay. So this is the value will be in meter square, right? Meter square per second. Right. Then we have to put the value of D in this equation. Right. Now we will be using this equation. Say for example the Cx, this is a concentration at a position 2.5, we know that 2.58%. Then we have summation of the two concentrations, that will be 5 plus 7, that will be 8, no 7, for 5 plus 2 will be 7 by 2, right? And then we have the subtraction of the 2, that will be 3 by 2. Then we have ERF function divided by 2 under root of D. This is your D value, that is 4 multiplied by 10 to the power minus 15, and you have to find the value of your time. So now you can tell me what is the value of your time. But before that, you will have to find a value of some ERF function, right? You will have something like this. You will have all of this value. You will have y or z, because we are using z here. So z is equal to ERF of z. So you have to first reach at this position, right? I think it will be 0.66. I'll try to solve it. It will be 0.6667. That will be equal to ERF Z. So then after that you have to use this table which is given here, which is the value of your Z and ERF. So this is 0.6667. So you have this value of Y. You know that ERF of Z is equal to 0.6667. So you have to find the value of this Y here. Once you find the value of your Y, then you can find the value of your time also. We have equated the point 66667 to ERF of Z. Once you get the value of because you do not know what is the value, what could be the value of this Y. So for finding the value of Y, you have to use the table, and by interpolation method we can use like this: Y minus 0.650 divided by 0.7 minus 0.65, that is equal to 0.6667 minus 0.6420 Then we have divided by 0.6778 minus 0.6420, right? Then you can find the value of your y. I will put it here so you can do it. So the value of your y will be something like 0.6844. So this is the value of your y, and that is equal to, because you have now solved the ERF equation, that will be equal to 393.8 under root of time. So you have to find the value of time. So what will be the value of your time?
Madam, in this calculation, what is 393.8? I didn't get.
The once you are solving it for the diffusion coefficient, like you are solving it like this, you are having this ERF of okay, we have not written it. ERF of this is actually ERF of x, right? The distance at which you have the diffusion. I have written only the half equation. So one second. You have equation like this. I will just write it in a better way. You have this value of Cx, and then you have a value of ERF, and then you have a function which is x divided by 2 under root of dt. Once you put the value of your x, because you know what is x, that is 50 micrometer. So you know the value of your x, you know the value of your d, you know 2. So all of this, when you solve it, you will achieve 393.8 divided by under root of t. So this is the solved value. Now ERF of something, that was ERF of this whole function, that was solved from the table. So you found the value of y from the table. So you equated y is equal to ERF of, or z is equal to ERF of z. So you know the value of your uh, ERF of z from this part, this whole of this is 0.667. You know the value of ERF z, you know this. Now you can calculate the value of y, and from interpolation you calculated y and put it here. So you now have a value of y equal to the function that was present inside ERF. So this was the whole function. So actually all of this is equal to z, right? You are actually equating this z is equal to ERF of z. What is the value of your whole function? So you have achieved this equation finally, and now you have to say what is the time required for diffusion.
33,100 seconds.
Okay. So how much time will it be, like in hours?
9.2 hours.
9.9.2 or 92? Are you sure? I think the answer is 92 hours. You can try verify it. It is the purpose of the question is how you find the value of your time that is required for diffusion for a two alloy system where you can have a diffusion of one atoms from one place to another, and then it will result in some diffusion coefficient. First to find the diffusion coefficient, and from that using the ARF table you can calculate the value of time that is required for diffusion. Okay. Then we have another question that says this is based on your this iron carbon diagram and the lever rule, right? So it is saying for a 99.65 weight percentage iron and 0.35 percentage carbon. So this is the composition of your alloy. Just below the eutectoid, the fractions of the pro-eutectoid ferrite and pearlite are respectively. So we have to find the pro-eutectoid. Because why? Because we are not at the eutectic point. What is the eutectic point for this? This is your iron carbon diagram. This is your alpha. This is something your 0.02. You can say it is 0.02, and you have this point which is 0.76, right? Because you know this is a eutectoid point for iron carbon diagram, right? And this is your some phase, and then you have a mixture of phase. Say for example you have alpha plus gamma here, right? And then here you have alpha plus cementite, you have ferrite and cementite here. So now it is saying for a composition of 0.35. So where is the 0.35? It is somewhere in between these two, so it is somewhere here. So this is your composition of given in the question, that is 0.35. So you are saying that at a temperature just below the eutectoid, so this is your eutectoid point, eutectic line, this eutectoid line, this, you have to say what is the just at below the eutectoid, the fractions of pro-eutectoid ferrite and pearlite. So you have to find what is the weight fraction of pro-eutectoid ferrite and what is the weight fraction of pearlite. You know that at eutectic mixture, when you have a solidification, you will have two phases. One is ferrite and one is pearlite. Like one is the gamma phase will be converting completely into your, say for example if we say it will be complete converting into ferrite and cementite, right? But here you are saying ferrite and pearlite. Pearlite is nothing but it is a structure, it is a eutectic mixture of your eutectoid. Whenever you have a eutectoid that is getting solidified, so you'll achieve a pearlite, which is a mixture of your ferrite and cementite. So because you are in a region which is hypoeutectoid, so you will always have some extra ferrite being formed, which is proferrite or proeutectoid ferrite. So that proeutectoid ferrite, you have to calculate what is that extra amount of proeutectoid ferrite, and rest of that will be the pearlite. So you can take 1 minute to solve it. It is simple because you just have to find the using the lever rule, you have to find the value of your proeutectoid ferrite and pearlite. So using, if you see this question, you have to find the proeutectoid ferrite. Obviously, here you have a mixture of both perlite and cementite. You cannot find using this area field. If you see but this area field which is just above the eutectoid point, you have alpha, which is your actually proeutectoid ferrite, and then you have gamma. Gamma is something that will be converting into perlite, right? This gamma will actually convert into perlite once you cross over the eutectoid region, while this alpha will remain as proeutectoid ferrite. This is possible because you are in a hypoeutectoid region. So just using the lever rule in this region, which is just above the eutectoid point, we can find the value of proeutectoid ferrite and gamma. Actually, we can find the weight percentage of these two phases, but based on the question, we understand that the proeutectoid ferrite is nothing but the alpha from this phase region, and perlite is nothing but the gamma that will be completely transformed to perlite once the eutectoid region is crossed over. So the alpha will be given by
Alpha comes out to be 52%.
52. So we'll just write it here. So the alpha will be given by 0.76, sorry, 0.76 minus 0.3, I think, yes, that will be 0.35 divided by 0.76 minus 0.02. So this is the value of your alpha, and for perlite the value will be 0.35 minus 0.02 divided by 0.76 minus 0.02. Okay, so you can find the values. So what is the value for the proeutectoid ferrite? 56%, I think, and this will be
55%.
okay, 55%, and rest of that will
45.
be perlite. Okay, then we have, this is I think the last question. Then we have, based on the stress strain curves, we have found many different parameters. So based on their graphs, you have to answer these. So it is saying, answer the following question regarding the four materials shown whose uniaxial tensile tests are shown below on a stress strain curve. So you're given a stress strain curve. Now first question says which material is toughest. So out of the four curves, like you have 1, 2, 3, 4 curves, you have to say which of the following is toughest based on the curves that you are seeing here, right? How do you define toughness? We define toughness for a stress strain curve. It is actually the area that is under the stress strain curve, right? Under a complete, including the elastic plastic region, all of it is a toughness. That is how much energy it can absorb in a material. That is just toughness. So which of the following will you think is having a more area?
Material 1.
Right, material 1, because it will have this much area and it will have a maximum toughness because the area under the curve is large, right? So 1. Then we have which material is strongest with respect to yield and with respect to ultimate tensile stress. You know that yield is a region up to which there is, if you unload the material will return to its original position, which is elastic region, right? While ultimate tensile stress is beyond the yield point, where it is the maximum stress that it can endure before the material actually fractures. So you have to say which is the strongest with respect to yield and which is respect to ultimate tensile stress. Yield means that it should have a higher elastic region, right? It should have a steeper slope. Say this is your elastic region, but it will read this is your yield point. For this material, the yield point lies here. For this material, it is somewhere here. And for 3, the yield point is somewhere here. right? So you represent, this is your yield. Yield is given by sigma y, right? So you can see for material 3, you have a highest yield, right? So for yield, we can write material 3. And for ultimate tensile stress, which is the highest, which is having a better UTS?
Number 4, ma'am.
Yes, because you see this material will fracture somewhere here, this material will fracture somewhere, say here, this will fracture here, while material 3 has already fractured at a lower point. So you can say this is your UTS. This is your sigma UTS, I can write it. Okay, so material 4. Then we have another question that says which material is most ductile. So when you say ductile material, that means the material that can undergo plastic deformation without fracture. So it will have a good plastic range, not a elastic range, but a plastic range. So which is the right option for material most ductile?
Madam, material 2.
Right. And what do you say about a material which is more brittle? Brittle is something where you say that the material has not endured a large amount of plastic deformation. That means you give it a plastic deformation, but it just fractures. It does not have a large, it does not undergo a large straining once you provide large plastic deformations to the material.
3.
Right, so the material 3 is having more brittle. Why? Because you tried to give it, see, for this you tried to give plastic deformation, but it endured for a longer time. For the same for 2, same for 1, same for 4. But for 3, once you gave a small amount of plastic deformation, it fractured just like plastic. So it just became brittle. So it is 3. Then we have a material, it says which material is stiffest? Stiff.
Material 3, ma'am.
Right, because stiff is something which is having a larger yield strength. Whenever you have a larger yield strength, you will have a, say for example, more stiff, or you can say the material which is having more steep this elastic range. So the material 3 will be the right option. Then you have which of the material is expected to have highest hardness. Hardness is actually a function of your, see, hardness is not given by your uniaxial tensile test, right? You separately do some hardness test on your material by using Vickers, Fresnel or some other material. But it can give you an idea that which can be a more hard material, right? Hard means something you are giving a deformation and there is a reflex from a material, it is not taking the deformation. So it is always with a material associated something with your yield stress and ultimate tensile stress, right? Yield stress or ultimate tensile stress. So you can say you can have a high hardness for a material, like for example material 3 or material 4. Anyone between 3 and 4 can have a large hardness because it can undergo plastic deformations, right? So the answer is 3 and 4. 3 or 4, any one of the two. But after that, we can do some hardness tests and determine the appropriate hardness. Okay, I think that is all for today. If you have any question.
Ma'am, I have a query from last Sunday's live session, ma'am. There was a question that the slip will occur at which plane?
Yes.
So the same question has been mailed to you also, ma'am. Please see and please reply, ma'am, because the same question has been asked in the week 7 assignment also.
Okay.
But the answer given is different from what you have said in the live session, ma'am. So there is a little bit confusion that which one is correct.
Okay, okay. I will try to see it. Okay.
Thank you, ma'am.
Okay.